jump into some spicier, newish stuff. Now, you have done an intro to magnetic fields, but that's where we're really going to kick off with some of the new stuff for this module. Now, magnetic fields are also vector fields, in the sense that they point in a particular direction, but unlike electric fields you could just have like a positive charge, and then the electric field just like goes outwards from there. Magnetic fields always have to come in dipoles, which basically means they have to have like a start and an end. They can never really exist just as like a positive side and a negative side. They always need to have a north and a south pole. So as a result, their field lines usually look like these nice little butterfly looking things, where they curve around from the north side to the south side. You can kind of imagine, if you could see inside the magnet itself, you can kind of imagine that the field lines would just sort of continue, and because I'm doing red on red, you can't really see it, but imagine that inside inside the magnet itself, they sort of continue back through from the south pole to the north pole, which is how these field lines don't just like exist as like north poles and south poles. They always have to go through in this nice complete loop. In module 7, you'll take a look at Faraday's laws, and the second one basically just says that they always have to come in dipoles. You can't have a magnetic monopole. A fancy way of writing it is this upside down triangle dotted with B is equal to 0. If you're interested in calculus and stuff, you can look up what that is. But aside from that, that's all I'm going to say about that. Now, one quick tangent on a little bit of notation with field lines, because what we're about to dive into is a little bit of three-dimensional field line forces crossover stuff. And because, to be honest, even though you've done like dynamics, you've done like kinematics and all of that stuff, a lot of the stuff you will have encountered so far is only two-dimensional. You haven't encountered a ton of stuff that's dealing with three dimensions, but in this topic, we are going to be really diving quite deeply into things that might be moving in multiple dimensions where we need all three dimensions. But unfortunately, our paper only, like our nice, neat screen and paper and stuff, only has 2 dimensions. So as a result, we need something to help us deal with the third dimension. So as a little bit of notation, we can write something moving into the page as a series of crosses, and we can write something that's sort of sticking out of the page or coming back towards us by a series of circles or little dots. So this basically just means that you can kind of imagine, instead of having like a field that's going over to the left, sorry, I say a field going over to the left and then draw one moving to the right, and a field moving over to the left or a field moving over to the right, you can imagine we've got one that's going directly into the page. It's like moving into the screen, whereas here we've got a field that's coming back out of the screen towards us. Now, I like to imagine that the way that I sort of visualize this and remember it in my head is I sort of think of like a bow and arrow. This is a very classic example. Your teachers would probably use the exact same analogy, and the reason is because it's a great analogy. You can imagine like a bow and arrow, right? Like those arrows that you shoot out of a bow. Here's my very dodgy drawing. That's horrific. Let's see. This is why I'm like a physicist and not an artist. This is why I didn't go to art school, guys. That's even worse. I am so. Welcome to Tim's art class. This isn't what you thought you signed up for when you came to my recording. But hey, it is what it is. Okay, imagine it's like an arrow, okay? It's zooming through the air. Don't judge me. It's okay. So imagine we've got this arrow and it's flying through the sky. If this arrow is coming towards you, what you're going to see is that little knob on the end, right? The arrow tip. You're about to die. But that thing coming towards you is a lot like that little dot that's coming towards you if a field is moving out of the page. Whereas if this arrow is moving away from us, what do you see? Well, you see a little fletching at the end. You see those little arrows that those little feathers that like the arrow maker has stuck into the end of the arrow. And that's what I like to remember when you see a field moving away from us. That's what these little X's are. They're the little fletching at the back of the arrow as it's going away from you into the page. So essentially, whenever we have something that's moving into the page, we can represent it with all of these X's, and whenever we have something that's moving out of the page, we can represent it with all all of these little dots. Most of the time, 90% of the time, this field is going to be a magnetic field. But the reason I want to bring it up now, and the reason I just want to emphasize the fact that it's just a field, is because occasionally you will actually have like an electric field, or hell, you could even have like a gravitational field that's moving in or out of the page. And so sometimes when you're doing your exam, like you get tricked by thinking, oh, it's an electric field, so it's like a magnetic field, when actually get pranked, it's an electric field and you've just lost a mark. So just keep that in the back of your head. Even though most of the time it's a magnetic field, it doesn't have to be a magnetic field. It can be an electric field as well, which is great. Now, one of the really interesting things about magnetic fields, right, is we've seen anything that has mass will generate a gravitational field. Anything that has charge will generate a electric field. But in order to generate a magnetic field, we need to get the charge moving. So basically, any charge that is moving is going to generate their own magnetic field. Now, I'm pretty sure I'll chat about this. I'm going to chat about this a bit more in just a second. But one of the ways, actually, I will chat about that later. I'll leave that for later. Sorry. And basically that magnetic field can like interact with external ones to create a force, or can interact, and when I say external one, I mean that could be a magnetic field of another particle, it could be a big external like huge magnet that you've got, it could be a bar magnet, but just like how when you've got two interacting gravitational fields, that creates a gravitational force, or two interacting electric fields, that creates an electric force, whenever you've got two interacting magnetic fields, that will also create a magnetic force as well. Now, the formula for our magnetic force is given like this. It's our magnetic force is equal to QVB sine theta. Ignore the sine theta for now, just focus on the QVB, that's the important part, where F is our force, it's measured in newtons. Q is our charge, it's measured in coulombs. V is the velocity of a particle, right? So this is why we actually, like, this sort of emphasizes why we actually need to be moving. Our particle needs to be moving in order to generate a magnetic field, because if it does, and like as a result, if it only experiences a magnetic force when those two fields like interact with each other, you actually need to be moving to experience the magnetic field force. And if you're not moving, you won't experience the magnetic field force. So that's the velocity of our particle measured in meters per second. B is our magnetic field strength. That's probably the only like really new one in this one, is our magnetic field strength. And if you can remember, it is measured in Teslas, which is a fun unit. Now, sine theta is a bit of a funky thing. It basically measures the angle between the magnetic field lines and the direction of your charged particles. So you can imagine if you've got some kind of magnetic field that's moving along like this, and let me change color real quickly. Okay, let me not change color, but imagine you've got some particle that's moving along in this direction. The angle between these two, that little theta here, is going to be the angle in that sine theta. As a result, if you're decently comfortable with your maths and trigonometry, you may notice that sine theta starts at 0 when the angle is 0, sine theta is 0, and then slowly grows up to 1 as the angle increases to 90 degrees. And so as a result, we actually get a maximum force when your magnetic field lines and your charged particle are moving at right angles to each other. So if they're perpendicular to each other, if they're moving perpendicularly, you get a maximum force. And if they're moving in the same direction, you actually don't get any force at all, right? Because theta would be equal to 0. It's kind of like if they're moving, if they're moving parallel to each other, you get no force. If they're moving perpendicularly to each other, you get a maximum force. Now, the funky thing here is the way that so that's how we calculate the force. But the really interesting thing and the kind of funky new thing with magnetic fields is the way that we figure out the direction of the force. And it's using what we call the right-hand palm rule, or at least what I like to call the right-hand palm rule. Because you may remember from year 11, you learned a little curly rule, which I like to call the grip rule. And don't worry, that rule is also very important, and we'll get back to that later. But for now, forget about it, all right? Imagine you never learned that rule before, except for the fact that it's like a right-hand rule. And basically, the way that we figure out the direction of this force is if you point your thumb in the direction of the particle's motion, you point the rest of your fingers in the direction of the magnetic field line, you can imagine that you're kind of like a little Jedi kind of thing, and the force is coming directly out of your palm, right? So it's pointing towards like wherever your palm is pointing. Now, one last little side note for that, and this is something that, once again, really, really super important that you get on top of because it's something that a lot of people make mistakes with. But this is only for a positively charged particle. For a negatively charged particle, because it's going to move in the opposite direction to an electric field, sorry, to a positive particle, instead of the charge coming out of your palm, it's going to come out the back of your palm. Basically, it's going to come out the back of your hand, shoot to wherever that is. If you really, really like on top of that, you feel comfortable with that, you can actually use your left hand instead for negative particles because basically it's going to give you the same thing. Just like if you want to test for yourself, right, you can hold both of your hands in the same position and you'll find that the palm of your left hand points in the same direction as the back of your right hand. But I would encourage you for the most part, just stick to your right hand because you don't want to accidentally like use your left hand when you're doing a positive particle, like whatever. And personally, to be honest, I'm a left-handed person, so I enjoy, not having to put my pen down when I want to do something, right? So I'm just lazy, I guess. I just always use my right hand rule. So just in summary, right, we can calculate the force using F equals QVB sine theta, which has a maximum when the direction of our particle and the direction of our magnetic field lines are perpendicular to each other. And also, as a result, we will get a force that's pointing out of our palm, wherever our palm is facing. Now, just as a quick practice for everyone who's watching the video, let's actually try using this. So I've got this situation here where I've got an electron. It's moving in a particular direction through a magnetic field. Remember, you can use your right hand palm rule to figure this out. So your thumb points in the direction of motion of a positive charge, your fingers point in the direction of the magnetic field lines, and your palm will show the force on a positive particle. So if you want to have a go at this question by yourself, feel free to just pause the video. But aside from that, let's jump into it. So the first thing that I would encourage you to do is actually identify, depending on how comfortable you are with this notation so far, is just identify, is this field going into the page? Is this field coming out of the page, right? So if you remember back to my arrow analogy, what we see here, what we're seeing is the like little feathers on the fletching of the arrow, which means that we're looking at the arrow as it's going away from us. So as a result, we can say that in this case, the magnetic field is going into the page. The next thing I can identify, so if you want to sort of keep track of it one by one, you can sort of point your right hand and you can point your fingers moving into the page. The next thing we need to do is identify what is the direction of the particle. Well, our particle is moving over towards the right, so you can flip your hand around and you can say, okay, my thumb is now pointing in that right-hand direction. Lastly, we then just need to figure out, okay, we've got the right direction of our magnetic field lines, we have the right direction of our motion. All we need to do is figure out the direction of the force as a result. And our palm is facing upwards. So we would think, okay, yeah, the force is pointing upwards. But you may remember from a couple of minutes ago when I said that's only true for a positive particle, which means in this case, because we've got an electron and an electron is negative, it's going to be going in the opposite direction, right? So instead of having a force going upwards, our force must be coming out the bottom of our palm, pointing downwards. And so as a result, we can say that our particle, our electron, is going to experience a force pointing down the page. So the sort of formal technical language that we use is we say that it's coming down the page, sorry. Another way you could put it is down the plane if you want to be like really super, super fancy. But those are the two main descriptions I would probably, those are the two main descriptions I would probably use to describe what's going on here. So yeah, just in quick recap, right? We've got our magnetic field going into the page. You can use your thumb to point in the direction the particle is moving. And then the force, because it's a negative particle, is coming out the back of your palm. And so that tells you which direction that force is going to be moving. Okay. Now that's out of the way, let's try and have a little bit of a practice of actually calculating that magnetic force strength, right? Not just using our right hand palm rule, but also trying to use that formula that we learned as well. So the formula, if you remember, says F is equal to Q times V times B sine theta. Now in this case, and the reason when I wrote this formula out for the first time, I was like, oh, don't worry about the sine theta, is because probably in like 80% of cases, you can just assume that your particle and your stuff are moving perpendicular to each other, because in most cases, they honestly are. Like it's not super common that they're not moving perpendicularly. That's not to say that it never happens. Like if you have a question that's trying to trick you, sometimes they'll be not perpendicular. Keep an eye on it, but for the most part, you don't have to worry about it, is what I would say. Now, in this case, because I forgot to when I wrote the question, we can just assume that they're moving perpendicular, and so as a result, we can get rid of that sine theta. Just once again, if you're confused about why we can do that, perpendicular means 90 degrees, sine of 90 is equal to 1, so it's basically just doing like q times b times 1, which means we can get rid of the sine theta, just so we don't have to write as much and it's not quite as gross, and I don't know, it's personal preference, okay. Aside from that, now that we know the formula, we've got the formula down. The reason I wrote that is because we're trying to calculate the magnetic field force. So let's chuck that down. Aside from that, let's chuck down all of the other numbers that we know. So we know that the magnetic field is 10 Teslas. So we could write B is equal to 10. We're also told the velocity of the proton, which is the velocity is equal to 1 times 10 to the power of 6. Which just leaves us with the charge of the proton. Now, you don't remember from year 11, a proton has the same charge as an electron. It's just that instead of the electron being negative, the proton is positive. So it's sort of like a positive version of whatever the charge of the electron is. And if you don't remember that, no worries, just flick over to our trusty formula sheet, scroll up to the data section, and it is in fact the top entry here. It's the charge on the electron as negative 1.602 times 10 to the negative 19 coulombs. But of course, because this is a proton, it's positive, so it's going to be positive 1.602 times 10 to the negative 19 coulombs. And yes, sorry, I should have included my units beforehand. Our magnetic field strength is 10 teslas. Our velocity is 1 times 10 to the 6 meters per second. And we can just chuck all of those numbers in. So let's say our magnetic field force is going to be 1.602 times 10 to the negative 19 times our velocity, which is 1 times 10 to the 6, times our magnetic field strength, which is 10 teslas. Chuck all of that in, and you get 1.602 times 10 to the negative 19 times 1 times 10 to the 6 times our 10 teslas, which if you chuck that into your calculator, you end up with 1.602 times 10 to the negative 12, and that's in newtons. Now, if we were given like a diagram, we could figure out what the direction is. But in general, if we haven't like this case, you probably don't need to chuck a direction in. But remember, because this is a positive particle, if you were to hypothetically, you know what, I'm talking about it. Let me just quickly draw up an example, all right? Let's say, actually, we've kind of done that one already. Let me, if you want to skip ahead like 5 seconds until I've actually drawn the question out, that's fine as well. I'm probably not going to add too much like crazy interesting insight, but yeah, let's say we've got a field that is made up of a whole bunch of little dots. And our proton, to spice things up, let's have our proton, lovely particle moving down the page like that. Which direction is our magnetic field force going to be going? Now, I'm sorry because I just wrote that question just then. It's not going to be in the little slider thing down below. However, this question would have. And sorry, I'm not sure if I mentioned it before, but basically, if you ever see a star in the side of the question, that means that there should be an associated Slido question. So even if I don't explicitly mention it, when you see the star, you can be like, let me go search. Let me go find this question down below so I can have a go at it myself. Anyway, now that I've got the question up, let's have a go at using our right-hand rule. So once again, we need to figure out, first of all, which direction is that magnetic field moving in? Because we've got all the dots. Remember, the arrow is coming towards us, which means the magnetic field is coming out of the page, which means you point your fingers back towards yourself. The next thing we need to do is figure out which direction the particle's moving in. It's moving downwards, which means point your thumb pointing downwards. And so now you've kind of got this weird, like, anyway, you've got this weird, like, hand arrangement. But the important thing is you can now see your palm is facing over towards the left, and because it's a positive particle, it means we can actually use our palm for the first time, which means our force is moving over towards the left. Is the direction that it is going to be pointing. But that's like one of the funny things with physics is you'll go into your physics HSC and there'll just be a point where like everyone's playing around with their hands, like it's the secret physics gang signs, right? Is all of the right hand rules that we have to play with, which is quite a bit of fun. But yeah, so our magnetic field force 1.602 times 10 to the negative 12 newtons, and it's pointing over towards the left in this specific scenario that I dreamt up. All right. Hope that is all lovely. Now, I've already had a little bit of a rant here about the sine theta, and the reason I'm not a massive fan of the sine thetas. I just want to preface all of this by this is very much my personal preference, and so if it works for you, it works for you. If it doesn't work for you, just completely ignore this, skip across to the next slide. But personally, I don't like all of the sine thetas and cos thetas, right? If you take a look at your formula sheet, if you take a look down here, there are so many cos and sine thetas, all right? I say that as not being able to find any, right? 1, 2, 3, 4, there's a cos squared, there's a lot of thetas and cos thetas and sine thetas, and there's another one there, and there should actually also be a cos theta at the end here. Sorry for this dodgy formula sheet. This is not the proper formula sheet. I'm sorry about that. Let me, just because I'm going to get annoyed, let's look up physics formula sheet. This is literally what I mean when I say look up the physics formula sheet. Let's find the actual physics formula sheet. This is the one produced by Nessa as well. Nessa, why are you like baiting us with this wrong formula sheet? Don't know what this is, but let me chuck in HSC to do this. Here we go. This looks better. And the Wi-Fi is just struggling. No, why is this dodgy? Okay, I'm sorry. We're gonna stick with this dodgy one for now because I can't find a better one. But your actual formula sheet, just in case you don't know what I'm looking for, it should be structured in different sections. It should have like the gravity section should have then below like the waves and stuff section, and then the electromagnetism section, and then down the bottom is the like quantum and special relativity and all that stuff, which is a lot of fun. Anyway, back to my aggressive rant on sine theta and cos theta. Basically, they're in all of the different formulas, and they all mean different things. Like sometimes they're talking about the formula, like the angle between two elements. Sometimes they're talking about the angle between an element and a normal. Like it just gets confusing. So if instead, the way that I would encourage you to do it is just try and do it through intuition. So if you remember that your force, your magnetic field force, reaches a maximum when your two things are perpendicular and reaches a minimum when your two things are parallel. You can just sort of remember that like that's the angle that we're dealing with, which is that the angle is between the like you have your maximum there, you have your minimum there. And if you then remember that sine reaches a maximum at 1 at 90 degrees and sine reaches a minimum when they're parallel, i.e. when we have 0 degrees, whereas cos has a maximum at 0 degrees and a minimum at 90 degrees. If you're ever sort of struggling to remember whether in a particular situation to use sine or cos and what angle to use, instead just kind of, I would encourage you to just remember like where do we get a maximum, where do we get a minimum, and that should direct you as to whether to use sine, whether to use cos, whether to use like what angle or whatever. If that all went over your head, don't worry, but this is just me saying, if you like sine and cos and you feel comfortable using them, this is your okay, this is your sign to just forget about them. No pun intended. If that all went over your head, just ignore it and try and memorize which sine and cos, that's fine. It's just, this is personal preference. I don't like remembering what sine and cos are. And so, just like when we encounter more sines and coses later on in today's lecture, that's why I'm gonna hate them, which should be a lot of fun. Okay, that pretty much brings us to the end of electric and magnetic fields. Just as a quick side note on how this lecture is kind of working, is I'm not going in every like single topic in a whole bunch of detail, just because like I probably wouldn't have time and this recording would be hours and hours and hours if I went through every single topic. So I'm just sort of trying to give you a taste of like the really important topics and give you a little bit of practice of the fundamentals. But just in terms of other things that you'll look at quickly in electric and magnetic fields, the big thing that you'll look at is the comparison between electric fields and gravitational fields and basically comparing the two. I've already done a little bit of that, but in terms of difficult questions, the reason that that can get quite difficult is the fact that you can have, just like how gravitational fields allow you to do projectile motion, electric fields can also give you projectile motion as well. And so if you see a question in an exam or something that has electric fields giving you projectile motion, don't stress. The only thing you need to do is you calculate the force, and then you can use Newton's second law, F equals ma, to calculate the acceleration. And then once you've got the acceleration, it's just you do the question as normal. Which is a lot of fun. One other last side note is that if you are particularly very clever and you've picked up on stuff nice and quickly, you may remember that you may have noticed that the force is always acting perpendicularly to the other two like objects, right? It's always acting perpendicularly to the magnetic field lines, and it's always acting perpendicularly to the direction of motion. It doesn't always mean necessarily that the magnetic field lines and the motion themselves are perpendicular to each other, but it always means that the force is going to act perpendicular to those two in whichever direction that they are pointing. If you're particularly eagle-eyed or eagle-brained, or I don't know, you picked up on it, this means that we've got a force that is always acting perpendicular to the direction of motion, which to those of you who have done Module 5 will ring some bells as the exact recipe required to give us circular motion. And as a result, we can say that our magnetic fields will actually give us circular motion. If you have a constant magnetic field and you've got a particle that's chilling in it and is moving around, it's going to move in a nice and neat circle. And that's something that's important. It comes up quite a bit in Module 8, but it's also a nice link between Module 5 and Module 6. It shows us that, you know, these things do actually come together a little bit. NASA isn't just messing around, even though sometimes it might feel like it. So with that,